hydrophobic portions. These are portions of the protein that don't like being in contact with the environment or in contact with the water. So it will actually twist and bend this protein in order to sort of present areas that like being in contact with the water on the outside, and areas that don't like being in contact with the water, it tries to move that towards the centre of the protein and avoid the contact with the water. So this is again just another instance of where we're trying to create an energy efficient structure. There is another term that we use, domain, and this is just more describes a sort of a particular area of that protein that has a regular shape, an identifiable shape. So you can actually have multiple domains within a protein, and examples of some proteins where you may have an extracellular domain, a portion of the protein that's exposed to the outside of the cell. You might have a membrane, a transmembrane domain, and you might have an internal domain. So this really just describes areas that have slightly different forms or slightly different purposes. And then the final level is what we refer to as the quaternary structure. So it's basically just a tertiary structure, but the reality is that these proteins don't exist in an isolated, they're always in combinations with other proteins. We're basically just a big bag of proteins all working together. So there has to be some way in which these proteins interact. So, we'll give them a name, we'll call them multimers. There's two proteins, it's a dimer, three proteins, it's a trimer, and so on. But when we talk about these complexes, we refer to as the quaternary structure that describes these complexes. And in this particular point here, I've written that it's hiding the hydrophobic portions of the protein. Probably a more important area is that it actually presents functional groups to the outside of the cell in order for it to do a job. So if we have something like a growth factor receptor, obviously there needs to be a portion sticking outside the cell that latches onto those growth factors. It doesn't make sense to have that growth factor receptor on the inside of the cell. So the quaternary structure is used to make sure that receptor is on the outside of the cell. And you'll notice in this picture here, it's unfortunately the picture on the left doesn't correspond exactly to the picture on the right, but in some cases you can see there that we've got those circular structures, the helices, and if you look particularly carefully, you can see that they have like an arrowhead here and so on. Now the beauty with proteins is that they're very consistent. They'll always form this structure, and it's because we have these protein sequences that sort of drive it to form a particular shape. Now when we treat it with formalin, we're actually cross-linking some elements within these proteins. We're actually deforming the shape of that protein due to the presence of the formalin. If we can somehow smash this complex apart and take it back to almost like its secondary structure, if we allow it to cool down and reform in its natural environment, it will form that exact same structure. So let's move on to what fixities are intended to do. I know it's a bit of a roundabout way of getting to the topic of heat retrieval, but it's important. So we've got a couple of reasons why we use fixities. The most important reason is that we want to try to preserve that structure to look exactly like it did in vivo. There's no point, trying to harvest a sponge and, we go and process it and then it basically just flattens out like a bit of bread. It doesn't retain that structure. So if we're trying to interpret that structure, we need to have it looking like it did when it was living. Another area is that we want to inhibit cellular breakdown. So the moment a cell dies, it starts to leach out all of its goodies from inside of the cell, and then other compounds and liquids will actually start to penetrate that cell. And again, that changes the cellular structures. So we want to try and prevent this autolysis from occurring. We also want to stop it getting extracellular damage. So this is damage from outside the cell. And if you want to think about this, it's probably clear enough if we talk about bacteria and fungi breaking down tissue. So if we left a piece of meat out on the kitchen bench for 2 days, it starts to rot, grows things on it. If we have this fixative in there, there's chemicals within that fixative that aren't pleasant for these microorganisms and fungi and multicellular organisms from growing on it. So it basically stops that damage from occurring. And then where it becomes important for immunohistochemistry is that we also need to make those protein structures inside those cells, they need to be preserved in their original state. We need to make sure that they don't dissolve and wash away. So the way that we do that is we can fix the tissue, and there's two major ways in which we do fixation. We can do a technique called perfusion, or we can do one called immersion. So in the case of perfusion, what we do is we take the sponge, whatever the host might be, and we dunk it into the fixative. Now I mentioned that the fixative inhibits cellular breakdown, it kills off bacteria. If I were to put a living organism in that fixative, then it's not really healthy for that organism. So we would typically do a technique called immersion, where we remove the tissue from the host. Those that have ever had a mole taken off or heard about someone getting a lump removed, Kylie Minogue would be a good example of that. That they would actually take that piece of tissue out and immerse that into the fixative, and of course that's much safer for the person donating that tissue. So there's really two major types. We've got cross-linking fixatives and we've got precipitated fixatives. Easiest way to think about this is you've got histology and cytology. That's a lot of the times where this distinction lies. So in the first case, cross-linking fixatives are predominantly used in histology. They're often, when we talk about cross-linking fixatives, they're aldehyde-based, so you've got things like formaldehyde, glutaraldehyde are the two most common ones. And then there's also one that we get used predominantly in research called paraformaldehyde. The glutaraldehyde is pretty much only used for electron microscopy, for routine histology, the clinical lab hospitals, research centres, doesn't use either formaldehyde or paraformaldehyde. And the way that these, as the name suggests, these cross-linking fixatives work is that they actually form bonds between amino acids within that structure, and that just helps to stabilise it. I've put a comment here that says that they're not all affected identically, and that's really important for when we talk about what type of pre-treatments we need to do on our tissues, because these proteins are not affected equally. They often require different approaches in order to get it to work. In the case of precipitated fixatives, these are typically just used for individual cells, not for tissue, but we can use things like ethanol, methanol, acetone, acetic acid, or combinations of those. So an example might be FAA, which is a formaldehyde, acetic acid and alcohol mixed all together. So it's really important that we fix tissues correctly, and there's a number of things that we need to do. So first thing that we need to make sure is that the tissue is not too thick. So if you imagine someone goes and gets a spleen taken out, a spleen could be the size of a large mango. If you were to try to put that into a container of fixative, it's going to take a very, very long time for that fixative to make its way to the centre of that organ. So we need to be thinking about what happens to that tissue that's in the middle in the time it takes for that fixative to get there. And you'll actually start to get autolysis and some of those other mechanisms affecting that tissue in the centre. So typically what they will do is that they will do a technique which they call bread knifing. And if you imagine you take a loaf of bread, you cut it into slices, the same technique would apply. And if we cut those slices into a centimetre thick, or ideally 4 millimetres thick, then all of that tissue then can make contact with that fixative and start that fixation process much quicker. The volume of fixative is really, really important. It's very, very common to see samples coming in from collection centres, from GPs and so on, and they've got a very, very small amount of fixative in it and a very, very large specimen. The problem is that if we don't have enough fixative, these fixatives are really dependent on the pH and the chemistry of that fixative being right. So if we were to have a piece of tissue that was, say, 1 cubic centimetre in size, and we put that in a container of fixative that has 1 centimetre, when that fixative finally makes its way into the tissue, it replaces the water that's in that tissue, we're effectively diluting that fixity 50% if we do this 1-to-1 ratio. However, if we do it 20 times, so if we have 1 cubic centimetre and we put 20 cubic centimetres of fixity in it, then it effectively works out to be a 5% dilution, and this is certainly a much more appropriate value for a change in that fixity. We also need to be aware of how long it's taken for that tissue from the time that it was removed for it to go into that fixative. So in the case here, you know, if we take a piece of tissue out and we let it sit on the bench for an hour, then all of those autolytic processes will start to occur. You know, you really want that tissue to go into the fixative straight away. But they refer to this warm ischemic time and the cold ischemic time. And, you know, the warm ischemic time is basically the time where it's taken out of the host and put into the fixative. And then the cold ischemic time is how long it's actually spent in that fixative. So in both cases, we want to try and make sure that the time before it goes into fixative is minimised, and that the time it's spent in fixative is appropriate for the size of the sample. In relation to that question about the volume of the fixative, we talk about this osmolality. So this is basically the osmotic potential of that solution. If we have a fixative that's too dilute, what happens is, you know, through osmosis, we'll have a purpose where the reagent is going to try and, the water is going to try and adjust or move into the area that has the higher concentration gradient. So if we have a fixative that's too dilute, what will happen is that water will try to go into the cell to dilute the cell, and that causes the cell to swell. In reverse, if we have a fixity that's too concentrated, the water that's inside that cell is going to migrate out through the cellular wall and try to dilute the fixative, and that then causes shrinkage. So it's important that we get this bit right. pH is ideally 7.2 to 7.4. Room temperature is always advised, although there are a number of sort of big private pathology labs that are working with microwave fixation and elevated temperature fixation just to try and speed up this process. And then, as you can appreciate, the duration would just be dependent on the type of fixative and the concentration that was used and how thick that sample was. So you'll often hear formalin being used as a fixative. I know I've mentioned it a few times, but it's important to understand that formalin really means a lot of different things to different people. So you have to be very careful what you ask for. If we look at the different formats, you can have something like a 37% formalin. So this is what we refer to as concentrated formalin. 10% neutral buffered formalin, 10% formalin, 4% formaldehyde, 4% paraformaldehyde, 4% PFA. With the exception of that first line, all of those remaining ones are exactly the same active ingredient at the same concentration. So when we go about making it, not Dako, but companies that make formalin, they basically take formaldehyde gas and they bubble it through water. That will come to a point of saturation, which is somewhere in the order of 37 to 40%. So if you think about that, that's our 100% formalin. And in reality, it's 37 or 40%. Then what we do is we take that 100% formalin and we dilute it 1 part in 10 in PBS to make our 10% neutral buffered formalin. But the active ingredient is actually somewhere in the order of 3.7 to 4% formalin in that 10% neutral buffered formalin. So you just have to be a bit wary that when you talk about this, that we're talking about the same things. If I go and say to, Daly to go and make up a 10% formalin, he should be asking me a few questions to make sure that what I'm asking for is actually, what it's going to make up and what I'm going to get. And when we talk about neutral buffered formalin, it's important to understand that fixative will actually penetrate very quickly, but the fixation process itself is quite slow. So although it takes a very short time for that fixative to get in there, we need to basically allow 1 hour for every millimetre thickness of the tissue. So if you've got a piece of tissue that's 10 centimetres, 10 millimetres thick, we're going to have to let it fix for at least 5 hours, because the fixative will come in from both sides into the middle in order for it to be fixed appropriately. But typically you're talking about for a normal, a pathology sample, somewhere between 6 and 24 hours is what's recommended. So I mentioned earlier that not all proteins are affected by the fixation process, and the reason for that is that these cross-linking fixities form disulfide bridges. Right? So there's actually only 2 amino acids that contain sulfur, cysteine and methionine, and it's only cysteine that can form these disulfide bridges. So if you have a protein that has a higher proportion of cysteine, then it's going to form more cross-links than one that has a lower proportion. If it happens to be that in that sort of 3-dimensional shape that we've got 2 cysteine right next to each other, yes, they're going to form a disulfide bond. But if they were spread, far enough away, there's a good chance that they won't be affected. But it really just depends on how much cysteine is in each of these proteins. And so, you might see a couple of examples here where that area might be, there might be 2 cysteines that is forming a bond across that sort of narrow gap there. So what does formalin actually do? So we've talked about that, that we form these cross-links, and these cross-links will cause that tertiary and quaternary structure to be changed, modified, altered. With antibodies, they will bind specifically to an antigen, or to be precise, an epitope, and it works like a lock and a key. That lock has the epitope has to be a complementary match to that antibody. If we change the shape of that lock, then it won't bind. So it's really important to make sure that we can do that. So antigen retrieval has a number of different names. All the ones up at the top are virtually the same technique. They're just called something differently. They'll even just get called retrieval generally. And that's because the enzymatic-based ones, the proteolytic-induced epitope retrieval, is not really a very common technique these days. Most antibodies will respond to heat retrieval. But to give you some idea, this enzymatic technique was developed back in 1977. So this gives you sort of a bit of an age of the antigen retrieval technique. With the enzyme, we really want to make sure that the temperature that we use is at the temperature of where the enzyme works optimally. So in the case of some of the earlier enzymes, trypsin and chymotrypsin were probably the first two. They're a naturally occurring enzyme in our stomach. So, it would make sense that they're going to work their best at 37 degrees. But in the case of proteinase K, this is derived from a fungus. Fungus don't have a natural, heat source. They're just relying to work at ambient. So obviously the enzymes that they've developed are appropriate for room temperature use. So really, the 1991 was the light bulb moment for immunohistochemistry. Prior to that, we had to be very, very careful in selecting antibodies. We had to design antibodies that detected an epitope that was not modified by formalin fixation. So the process for doing it was much, much longer than it was to produce antibodies these days. But Shen Shi was the first to describe this method, and he actually used a microwave oven to heat up tissue sections. In that paper they actually described using citrate buffer, but sort of prior to that there were some solutions used such as mercaptoethanol, urea, and these are pretty aggressive protein producing agents. But we're lucky that urea never became a good example of routine use one. I can imagine someone's going, look, let's think about this. What's a good form of way that we can modify protein structures? How can we reduce them at rate points? I know, I'm going to boil urine in a microwave oven. That's literally what they were doing. So we're very lucky these days that we've got things like citrate and tricity-TA buffers to work. So as I said, the most common one that we use today is a tricity-TA buffer. This probably works around about 80-90% of antibodies, and this has a pH of 9. That earlier one, the one that Shannon Shi described, is a citrate buffer around about pH 6. And with these images, I don't know if they show up that clearly. The one on the left was treated with low pH retrieval, the one on the right was high pH. Every other condition was exactly the same. So you can sort of appreciate how, with these advances in these techniques, that we can suddenly go from a very weak-looking stain on the left-hand side to something that is much, much stronger. So with antigen retrieval, these techniques are really based upon a number of factors. We've got the chemical composition of the retrieval buffer, through CDTA or citrate or urea or whatever. But time and temperature is really quite critical. We need to heat these solutions up, and you can see that the time and temperature is inversely related. So if we were to do a technique at, say, 125 degrees, we'd be doing it maybe for 30 seconds. If it was 121, 5 minutes, what we're doing today, or what we've already done, is the 95 to 99 degrees for 20 minutes. But if you wanted, you could go down to as low as 60 degrees, but you'd be looking at doing that technique for maybe nearly 2 days. So obviously in a modern clinical lab, no one's happy to wait 2 to 3 days for a sample run. So those for the timers that are going off, what you're going to do is you're going to be tapping off the excess, putting it into wash 1, and then moving it over to wash 2 after 3 minutes, and then stop at step 11. Okay? So so the mechanism here is that we don't really understand exactly what's happening, but we know that those protein bonds are being sort of disrupted in the presence of the active ingredients. Now this is the last slide, so you just have to be aware of my awesome MS Paint skills. Right? This is probably the most critical one in the sense that, we have these, the key messages here are that these disulfide phosphates are formed in the presence of that formula, right? That changes the tertiary and quaternary structure. So we've got our native protein on the left, we've got our modified protein in that second squiggle. We know that the heat and chemical composition will change that structure and basically causes those proteins to become disassociated. And then if we allow those proteins to cool naturally, and because there's no fixative around, they'll actually reform their original shape. And of course, if that original shape is there, then that antibody can bind back to its lock as it did in the first case. Questions?